This conference will now be recorded.
Very good evening, students. Today we'll be completing this electric potential part, and in the previous class, if you remember, we had discussed about electric potential due to a disk. How to calculate electric potential due to a disk? We had already discussed that. Okay, so just to recap, so what was the formula? We'll write down this formula. The way we had done is, see, whenever we calculate electric potential, see, electric potential can be calculated. So this is as a function of x. Okay, so it is the charge, if the charge is constant, divided by 4 pi epsilon naught point charge, for a point charge, epsilon naught x. Okay, at certain distance x from a point charge. So in this case, one point you need to remember is that this distance x is always constant. Suppose I have a point charge here q. Okay, I am calculating electric field at this point p, which is at x distance. This x is a constant distance. So this is important. This is important to calculate electric potential. This is constant distance at a particular instant when I'm calculating the electric potential at that point P. And obviously that is true for electric field also. So see, in this case, we are calculating electric potential on the axis of a uniformly charged disk, on the axis. So in this case, what we had done, we had just considered a ring of radius r. Disk means disk is composed of a ring. Disk is composed of a large number of ring. Large number of ring. So this is very common idea, fundamental idea for getting a disk out of a ring, because this we will be discussing while calculating center of mass, while calculating moment of inertia, while calculating electric field or potential. So in each case, disk will be composed of large number of ring, and disk is a solid matter, so it has matter everywhere, starting from this r is equal to 0 to the whole. Okay, so it has area, mass density, charge density, surface charge density. In this case, in case of mass, surface mass density. So surface, in this case, surface charge density, and uniform surface charge density. Okay, so this has uniform charge density, surface charge density, and that is denoted by sigma, that we had already discussed. So I'll just give you just a hint of what we had done. So electric field due to this elemental ring, potential, electric potential for this elemental ring is dV. So which is which is given by the charge which is held in the ring, dq by 4 pi epsilon naught r in the sense. See, if I say this is the distance, so look, this is the part. If I just consider this is the ring, so it is actually in the vertical plane. So this will be actually, just a minute. So kind of the distance we will get, actually the distance is this from here, point P. If I just draw a solid line, it will be somewhat this. So this is the distance. If this distance is some, this is x, this is small r, let us say this is capital R. Okay. So in that case, what will be the distance? The distance will be this r. This r is dq by 4 pi epsilon naught. R is square root of x square plus r square. Okay. So this was the thing. Now here what we had to do, we had to find out what is dq. So dq sigma into area. So what is the area? Area will be 2 pi r and dr. This is the area, sigma into area. And if we just put this value here, what we get? 2 pi r sigma into 2 pi r dr divided by 4 pi epsilon naught square root of r square plus x square. Okay, so this we can, okay, so the sigma and 2 pi can get cancelled, so sigma by 2 epsilon 0, and here it was r dr divided by r square plus x square and whole, this is square root. So you know that day we had, what we had done, we had actually we have to integrate this to get the total potential due to the whole disk. So this integration will go, see the small r will go from 0 to capital R. Okay, this integration we had to do, and see what is the integration here. So sigma by 2 epsilon 0, this is constant part, this is 0 to r, and r dr divided by square root of r square plus x square. So r square plus x square, so you have to take some trigonometric function, sec square theta plus tan square theta, right? Sorry, sec square theta minus tan square theta, this will be is equal to 1. That means sec square theta is equal to 1 plus tan square theta. Okay, tan square theta. So you could take this r as, or x, you can take x is equal to r tan theta, and then you can just do this integration. And finally, what the value we had got? We had got the value for this potential. So I'm just erasing everything, keeping except okay, I'll just keep the last point. Okay, so this we get sigma by 2 epsilon 0. We'll just keep the integration, small r is equal to cap. Okay, so r dr square root of r square plus x square. Okay, so if we do this integration, what we get? Sigma by 2 epsilon naught whole into, okay, by the way, this small capital R is the radius of the disk, say. So this is capital R. Okay, so what we had assumed, this one you can take any arbitrary value y. So y is equal to this. All right. So here what we are getting, r square plus x square. This is minus x. So this was the value of the electric potential due to a disk, and where it is the value at, so it is the value at any axial point to the disk. This is the value due to any axial point. And you know we can just calculate some two special values. When x is equal to 0, that means the center, at the center of the disk, x is equal to 0. Okay, v, the center, what will be that will be sigma by 2 sigma r or sigma by 2 epsilon 0 into r. Okay, so that is the central value of the electric potential at the center. Okay, and what else? All right, so these are few things, and see if this x is, say x is much greater than r. Okay, x is much greater than r. In that case, you know what will be the case? Uh, this r can be neglected, so this will give you 0 actually. Let me just cross check whether that is true. Okay, so electric potential at much, okay, so it can be actually, see if this is this, then we can actually take this part. We can just take here r square plus x square. So let us take x square common. So x will be, this will be 1 plus r square by x square whole to the power half. Okay, up to first approximation, x 1 plus 2 r square by x square. Sorry, this is half, half of this. So if we just put the value and then get the value of potential, see this x is there and here 1x is there, that will get cancelled. So sigma by 2 epsilon 0 into this will be r square by x square. Okay, r square by x square, and there will be some x multiplied, yes, this x is again there, so this will be actually r square by x. Okay, so 1 2 will be there here, 1 2 will be 2x, so this will be 4 epsilon 4 epsilon naught x. So if we just multiply pi, uh, so you will get pi r square means area of the disk, so it will be q by 4 pi epsilon naught x. So this is kind of a point charge. Okay, so at very far distance from the disk, the electric potential on the axial point will be just like a point charge. That means the whole disk has has a charge at the center. Okay, concentrated at the center, kind of that. All right, so we have, I think this portion has become too much messy. I'll just do it quickly. I'll just show you. I had already discussed. I'll just write down quickly. So second point, if x is much greater than r, so the term this could be simplified as the x square take common, so this will be 1 plus r square by x square whole to the power half. So this could be, this is fine, up to this is equal, and this could be written as x into 1 plus r square by 2x square. Okay, if we multiply, this will be x plus r square by x. Now you take this value, put this value here. So what you get, v x much greater than r on the axial point. So sigma by 2 epsilon 0. So this and this will cancel each other. So that's why I had written r square by x. Now if you multiply pi into r square into sigma, this is the total charge. Pi r square means area of the disk, into sigma, that the total charge on the disk, divided by, so 1, I'm sorry, here half will be there. So this will be 2. So 4 pi epsilon naught and x. So this, see in the numerator, this is q, and here 4 pi epsilon naught x. Okay, so this is what I had written. All right, so what you need to remember, this is on any axial point. So far we had already learned potential due to disk on disk at a point on the axis as sigma by 2 epsilon 0 whole into square root of r square plus x square minus x. Okay, so this is the value. Now what we'll do, we'll actually calculate electric potential at any point on the edge of the disk. You might be thinking, what is this? Edge point means what? Suppose this is disk roughly, so disk will have some thickness as well. So this is thickness. I'll show you three-dimensional figure. Anyway, so this is a disk, and everywhere there will be mass anyway. There will be mass everywhere, okay? Or here in this case, there will be charge on the disk. So we have calculated electric potential due to this disk at any axial point. But if my point is here somewhere, just at the edge, suppose this is the point P, and this is the center of the disk. So what will be the electric potential at this point? So this point is called edge point, okay? So electric potential on the edge of a uniformly charged disk. So surface charge density sigma say in this case also. Okay, I'll show you better figure here. I have better figure. Let me show you. Okay, so this is the point. So let us just take this disk, and at this point P, which is edge point. Okay, this is edge point. Edge point. Okay, this one is edge point on the edge of the disk. What will be the potential due to the whole disk? So in this case, as we were thinking that a disk at disk can be considered as a collection of rings. Okay, rings, right? So here what we do, we just consider such elemental ring. Actually in this case, a ring will not be the complete. What I am doing, I'm just considering here an elemental ring of radius r, okay, and thickness, ring has some thickness say, or I can say I just consider a ring, elemental ring of radius between r and r plus dr. Okay, between r and r plus dr, you look this. So, and see this ring has center at P. This is very important. So now I'm considering elemental ring of radius r. So this is elemental ring which is in between r and r plus dr. See this much distance. So this much distance is r, and this distance is dr. So up to here it is r plus dr. So I hope you have understood this. So from this figure it is very clear. So okay, and this is, see, in this case, see here one point you should remember. In this case, ring is not complete. Not complete. I mean to say, we can have an arc of the ring instead of the full one. Okay, because see, I have considered the ring in that way, because if I take this as center, then see, half of the part is here somewhere like this, isn't it? Half of the part is outside the disk, so don't bother about that point. So what I wanted to say is that the ring is not complete, so it is kind of an arc. So I'm just getting as an arc like this, okay, this is an arc. Okay, so this is an arc. So by the way, I'm just taking this angle theta. What is this angle? Suppose the arc and this radius of the arc, making an angle theta with the diameter of the disk, so this is diameter up to here, this is here, diameter will be 2r up to here, up to say PC is, see here, PC is r, that is the radius of the disk. And in this case, look, if I take this element, so why I have taken this element instead of taking the whole ring, why I have taken this element in this way, keeping this P as center? This is a good question. Why I have taken this ring keeping this P as center? Because see, when I calculate potential as a function of R, this R at any particular point should be constant. Okay, this particular, if I take any arbitrary ring, the distance varies, then we cannot write this. See, we cannot write q by, let me write kq. K is the constant. Okay, so I cannot write this formula as kq by r square, sorry, r, kq by r or kq by x. I cannot write in that case if the r varies. But in this case, see, since this is the center, P is the center, and this is the R of the ring, then see, every part of the arc or ring or elemental part of this is actually having distance r. So this distance is constant. Then I can just use this formula. Okay, for this elemental ring, I can actually write dq by r. Okay, so this is why I have taken this arc instead of taking the full ring itself. Okay, now I have considered this edge of the element is making an angle theta. See, suppose this angle theta, that means, you know, if I just draw this line, so this also will be theta. That means, you know, this arc is making an angle 2 theta, at P. This arc is making angle 2 theta at P. Okay, so these are few points we should remember. Now let me just copy this figure to make you understand in the next page. Okay, let us go here. So now we have to calculate electric potential first due to, let us write electric potential due to this elemental ring. So electric potential due to the elemental ring. Okay, so what is the distance? I know that is r. So what is the, let me write it first. dv, let me think that the potential will be dV due to this elemental ring or part of the ring. So I can write dq. dq is the charge on the whole element, and 4 pi epsilon naught r. So this is the formula, simple. But what is this dq? Suppose the surface charge density is given as sigma. So I need to write dq. What is the dq? dq actually, dq is here. This is this is having surface area, right? So what is surface area? This thickness is fine. What is the length then? So length I can calculate like this. So this is theta. So this is 2 theta. So what is this length? R2 theta. So R into 2 theta. This is the length. And what is the thickness of this? So length and breadth. This is kind of a rectangle now. Okay. So R2 theta is the length of the arc, and this dr is the thickness. So what I can write, 2r theta. Sorry. Yes, 2r theta into dr. So this is the area. First of all, this is the area of the element. Okay, if this is the area, now how to find out dq? dq sigma into dA. Okay, so sigma is sigma anyway. Sigma is surface charge density. This is 2r theta. This is dr. So I hope you have understood this. Otherwise, you might be thinking 2 pi r dr. Okay, 2 pi r dr, because here we are not getting the full ring. That's why it is not 2 pi dr. Okay, this is not 2 pi r dr. See, in case of ring, generally we write 2 pi r. R means the radius of this. Generally r sine theta. Okay, r sine theta and dr. Like that we write. So in this case, this cannot be written. This is for spherical shell. So here it is actually we are doing for thin disc. So in this case, you just take this strip as rectangular strip, and you can write length into breadth. So that is what I have done here. So dq I have got. I can just write once. So sigma 2 r theta and dr. This is the dq divided by 4 pi epsilon naught r. So here, look, this r and this r, I can just cancel it out, doesn't matter. So theta and dr divided by 4 pi epsilon naught. Now look, here there are two variables. See, theta can vary element to element. Okay, theta can vary element to element, as well as r, small r, can vary. Okay, so these are interrelated. So we have to actually bring this theta and r as a single, like only one variable, so that I can integrate it. Okay, integrate over a single element. See this, I just want to make in terms of theta, so that we take, see, theta we can take limit, so 0 to, so 0 to, see, 0 to 90 degree. So it is theta. See, at this point theta is 0. Okay, if this element is this, theta is 0, then it goes on increasing, and at this point when I take the strip, the angle will be 90 degree with this. Okay, so 90 degree. Okay, so in that sense theta can vary 0 to 90 degree. Okay, let us see. Okay, so first of all, let me write this integration. So b will be integration r 0 to capital R. So capital R is the radius. If I take my element at this r is equal to 0, then I am here. If I just go on increasing like this, like this, like this, like this, if I go on taking at different distances from the P, then I actually can cover the whole disk. So that's why R limit I can write. I can write the limit for this R as sorry, small r 0 to capital R. Okay, and this part is already there. So this is dv 0 to capital R, this one. Now look, I am doing integration over R, but there is theta here. So how to eliminate this theta, or how to eliminate one among this R and theta? So we have to find out some relation between theta and R. See, look, this is an arc. This is an arc. Okay, this is an arc. So this length is 2r. Okay, this is diameter of this. So if I think that this 2r is making an angle theta with small r, then I can get a relation, right? Okay, so I'll just show you here. This is 2r and this is r. Okay, like this. So this 2r is making an angle theta with this. So I can write r is equal to 2r cos of theta. Okay, I hope you have understood this. This smaller, so this is smaller, this is 2r total up to here. Okay, if I write this d, so PD is making an angle theta. So I can take a component. So this small r can be written as PD, or 2r cos of theta is equal to small r. Right? I hope you have understood this. I'll rewrite this. So small r will be 2r cos of theta. So then what will be dr? Dr will be minus 2r sin theta d theta. Okay, minus 2r sin theta d theta. All right, so now I can take the limit also from here. See, this is r, this is theta. So when r is 0, see, when r is 0, cos theta, so it will be 90 degrees, theta will be 90 degrees. When r is capital R, so it is small r is capital R. I think this will be 2r, not r. This will be up to going up to 2r. 2r. So small r will be 2r. So when small r is 2r, then cos theta is equal to 1. 1 theta is equal to 0. So if I do the substitution, look, I have got the integration sigma theta dr. Here r goes 0 to 2r. Okay, by 4 pi epsilon naught. This I have substituted. Okay, I have substituted r, small r, by 2r cos theta. So dr will be minus 2r. So let me write integration limit. I will take later. 4 by sigma by 4 pi epsilon naught. This is a constant term. I don't mind. So theta, let it be there, and dr is actually minus 2r sin theta d theta. Okay, so what is the limit now? Theta limit we have already found out. So when r is 0, theta is pi by 2. So r is 0 means theta by pi by 2 here. And when r is 2r, then theta will be 0. So look this, now I have got, see, r is the radius of the disk. So this is not a variable quantity. So I can just take this out. 2 sigma r, or let us write this sigma r divided by 2 pi epsilon naught. Sigma r divided by 2 pi epsilon naught. Here it will be theta sin theta d theta. This 2r we have taken out already. The 2 get cancelled here, so 2 pi sigma, here it is r. Okay, now we have to just see there is a minus sign over here. If I just interchange the limit, so theta is equal to 0 to pi by 2, 0 to pi by 2. If I just interchange the limit, then this will be plus. Now my problem is to solve this integration. Integration I, let us write this integration I. Theta is equal to 0 to pi by 2, and this is theta, sine theta, and d theta. So such integration could be done by could be done by integration by parts. Integration by Okay, so I don't know how long it was not there, how long I was mute. I'll just repeat a little bit. So this up to here, I hope you have heard. So this is the term which I have to integrate. I'm just doing integration by parts. So I'll just consider this as first function. This is second function. So I'll keep this and integrate this. So there will be minus sine cos of theta, and this theta will have limit 0 to pi by 2. And see, theta is 0. When theta is 0, this term is 0. When pi by 2 is 0, so this term will be ultimately 0. Then minus sign, theta is equal to 0 to pi by 2. And here I have to first do the derivative with respect to theta. So it will be 1 into, say, integration of the sine theta, that will be minus cos theta. And further integration. So this first term will be 0, and this minus and minus, this will be plus. So I have got theta 0 to pi by 2, and it will be cos of theta integration sine. So this will be ultimately sine theta and limit 0 to pi by 2. Pi by 2, 0 sine theta, sine 0 is 0. So pi by 2 will be giving you 1. So this part, after integration, this part will be 1 only. So this is sigma r by 2 pi epsilon naught. Okay. So dear students, you can see how we have calculated this. Sigma r by, I think there was a 2 here, right? So there was a 2 here. This is 4. Let me just go back to our sine theta. And here in the area also there was 2, right? There was 2 here also. So this, there will be 2 here, and 2 are cos theta. From there also 1, 2 will be coming. So I think this 4 will be, so 2 sigma it was, 2 sigma here. This 2 also will come into picture. So this 2 will not be there. So otherwise things are fine. Okay. So I have just skipped this to, okay. So this will be sigma r by pi epsilon naught. So this will be the value, and you can see that value will be always constant on the surface. On the surface, it is on the surface or on the edge. So this is the 1. This is the 1. So this is the potential at any point on the edge of the disk. Sigma r by epsilon. So all are constant. You can see this is a constant value. Constant value. So if you remember what was the value at the center for this, see at the center x is equal to 0, so sigma r by 2 epsilon 0 it was. So sigma r by pi epsilon 0, so this value is actually less than the previous one also. Okay, so this is, so I'll just write down, I think I'll write down the two outcome together. Let me go back to this. Okay, all right, so two results if we write down, let me write down first two results. Okay, just forget about this now. uh, so potential axial due to a disk axial point, it is actually sigma by 2. So look here, sigma by 2 epsilon 0, this value, sigma by 2 epsilon 0 whole into square root of radius square plus the distance square minus the distance x. And in this case, at any point age point, so this is sigma by pi epsilon 0 into r. So this is actually on the age. So potential, electric potential due to a disk Okay, so these are two important points to remember. Okay, all right, now I'll just clean this portion because I have to solve this problem. What we have in the background, you can see this. So we'll now solve few numerical problem on electric potential. See, the first problem says first problem says find out the point on the line joining two charges. See, there are two charges, plus q and minus 3q, kept at a distance 1 meter away, where the electric potential will be 0. So you have to find out the point. You have to find out the point where, so point on the line joining the two charges q and minus 3q, where the potential will be 0. Look, I can show you here. So this is the plus charge, this is minus charge, and see, we'll just take the magnitude of the charges. Magnitude wise, this charge is more than this one. So we had previously discussed, if you remember, the point where the potential or field, any case, potential or field will be 0 must be near to the smaller charge, near to the smaller charge. So this is one point to remember. So I'm just considering, see, that near point can be outside these two charges. So it can be, or I can say left to this positive charge q, that is at r distance. I'm just considering a point which is outside these two charges, and that is, see, why don't I consider here? Because because of this point, generally the point where the electric potential or field will be 0 due to these two charges will be nearer to that point will be nearer to the smaller charge. So when I am considering a point outside these charges, then I need to take in this, at this position itself. I cannot take this is the position P where the potential is 0. No, that we cannot take, because we have to take the near the smaller charge. So I am taking the outside point. So outside. Okay, point outside. Now I can take, okay, let me write this thing, like electric potential 0 means sum of the potential at this will be 0, right? So sum of the potential, so potential due to plus q will be q by 4 pi epsilon naught r from here, and due to this will be minus 3q by 4 pi epsilon naught r plus 1 meter plus r. So this is the thing. Now this will be 0. So if I just do this calculation, look, this part from both sides will be 0. This q will be going. So this will be 1 plus r is equal to 3r. Okay, so that means it will be 2r is equal to 1 or r is equal to 0.5 meter. Okay, so this is one part. So if this is outside point, then from q it will be 0.5 meter to the left. Okay, to the left. Now if I take any point inside, let us say this is the point where the potential is 0, and that is also near the smaller charge. Okay, so then this distance is automatically 1 minus r, right? So I can write here also q by 4 pi epsilon naught r minus 3q by 4 pi epsilon naught 1 minus r, right? So here also this point, this will be cancelled out. This is 1 minus r is equal to 3r. That means 4r is equal to 1. So that implies r is equal to 1 over 4. So this is 0.25. Okay, that means there are 2 points. There are 2 points where the potential can be 0 due to these two charges. One is at the left of this positive charge. How much distance away? That is 0.5 meter away. And one point could be in between these two charges. In between these charges, and that distance will be 0.25 towards the right from this positive charge. Okay, this I can say inside. So inside. Okay, this is towards right to the positive charge, and this is towards left to the positive charge. Okay, so this is the thing. Now I can just take 2 more numerical problems. Just quickly I'll take, and then I'll stop. See, electric potential in a region is represented by this. Then obtain the expression for electric field strength. How do you calculate this field strength from this potential? See, to do this, we need to know the relation between potential and field, electric potential and electric field. So I'm just omitting the electric part, electric one. So there is a relationship. How do you get? E is equal to minus dV dr. Okay, E is equal to minus dV dr. All right. See, let me just write in Cartesian dV dx. So if this is so this is in a one dimension, 1D, one dimension. But suppose the potential is given as in terms of 3 dimension, then how do you do that? This could be written, see, ex I cap plus ey j cap plus e z k cap. Okay, so this electric field also will have 3 components, ex, ey, ez. So ex can be found out by writing dv by dx. Ey could be found out dv by dy, and Ez could be found out minus, like found out this. Okay, doing this. Now in this case, see this electric field. So this potential is given in the 3 dimension. So I can find out component of electric field along x-axis. So the dv dx, that will be 2. Okay, and Ey will be 3. What will be Ez? Ez will be minus 1. So what will be the electric field strength then? Electric field strength in vector notation we have to write. First of all, if I have to find out the expression, they have asked you expression, not the magnitude. So expression will be, see, 2I cap plus 3j cap minus k cap. So this will be electric expression for the electric field. This is expression for the electric field. If you are asked to find out the strength or magnitude of the strength of the electric field, then you have to take the mod of this. Okay, we'll have another point. So as I was discussing, that if the potential is given in 1 dimension, then I can directly write this Ex. This will be always in the x cap direction. So Ex. So electric field will be this. So minus dv dx I cap. So minus, so dv dx means 8x. Okay, x I cap. So this will be the value. See, this is, see now values, points are given again. So this is at 1 meter, 0 and 2 meter. The value you have to find out. See, there was x over here. So this is x. So x is 1. So it will be minus 8I at this particular point. Okay, so this is actually electric potential. Now if I have to do the reverse, if I have to do the reverse, we can just do the reverse also, right? So if I have been given the electric field, then I have to find out the potential. So how do you do that? So we know E is equal to dv dx. So I can see in 1 dimension, I can write dv, so dv is equal to minus E dx, right? If I have to find out the whole one, then I have to take the integration of this. That means integration minus E dx. So this integration we have to do. Now this integration could be done in 2 ways. So like say 2 ways in the sense, I can just take the components Ex dx like that, or I can do directly. How to do? How do you do directly? E dot dr. So B will be integration E dot dr. Then so then x, y, z and all, there will be values if you take the value. So this dr, so this E has all the components. So Ex I cap plus Ey j cap plus Ez k cap. Okay, and you know this also you have to write in terms of component. Okay, so I dx plus j dy plus k dz. So like that we have to do and find the value of potential. Okay, so this we will do in the next class. So we'll take up example related to this, and also we'll move further. We'll just discuss equipotential surfaces, etc. in the next class. Okay, so thank you for your patience. Bye for today.